Hi everyone, welcome to Mostly Math. Today we'll be investigating the meaning and the derivation of the statement that energy is conserved for a harmonic oscillator, which we are going to abbreviate HO. So HO stands for harmonic oscillator. Okay, what exactly is a harmonic oscillator? First, well, we typically model the harmonic oscillator as being some kind of mass attached to a spring here, and there's going to be some kind of a characteristic time for it to return to its endpoint once it starts oscillating. And this characteristic time is going to be embodied in the constant omega, or the angular frequency, which if you wanted to, you could write in terms of the mass of the particle and the spring constant. But we're not going to be using that in this video. I just wanted to bring that up. Okay, so harmonic oscillator is a mass on a spring, and it just goes back and forth forever, basically. And what does it mean for energy to be conserved? Well, one of the consequences of classical mechanics is that you can show that in any closed system, energy is going to be conserved. What this tells you is if you take energy as the sum of some kinetic energy plus some potential energy, then we're going to have the time derivative of energy, or E dot, same thing as dE by dt, is going to be 0. This is just in very general terms here. And we want to show that this is true for the particular system of the harmonic oscillator, which is not too hard actually. So let's begin. So first we have to define what we mean by harmonic oscillator mathematically, now that we know what it is physically. I'm just going to start by the simplest definition, which corresponds to what I indicated earlier about it oscillating back and forth from start to end forever. This tells us that the harmonic oscillator position, x of t, is defined to be some constant a, representing the amplitude of oscillation, times a sine function of the angular frequency times time plus some offset delta if it doesn't start exactly at 0. And this, for our purposes today, can be considered the mathematical definition of the harmonic oscillator. If we look at the graph of the sine function, certainly has the characteristics that we want. It just oscillates forever, starts at 0 or some other offset, reaches a maximum and a minimum, comes back to 0, does this forever. So intuitively it would make sense that we could represent harmonic oscillators by the trigonometric functions. There are of course other ways to write it. You could easily write this in terms of a cosine, and you could even write this in terms of, sine of omega t plus some other constant times cosine of omega t. So you could also write it like this, some constant plus some other constant. If you wanted to have a pure trigonometric form, and in fact you would typically derive it in this form by solving the differential equation, which we'll get to in a moment, and then realize that you can simplify your life by using a trig identity to write these constants in terms of just an offset here. So just some background. This is the definition of the harmonic oscillator. Let's start by taking derivatives. X dot is then going to be a omega sine omega t, sorry, turns into a cosine omega t plus delta. And now, just for fun, we're going to take a second derivative and see what kind of a differential equation this can solve. Second derivative is going to be minus a omega squared sine of omega t plus delta, which, of course, you can recognize is proportional to the function itself. It's just going to be minus omega squared x. So this shows us that our original definition satisfies the differential equation x double dot plus omega squared x is equal to 0. And if you wanted to start by defining this as the harmonic oscillator, you can totally do that as well. Why are we taking derivatives though? Well, we're taking derivatives because the kinetic energy is going to be 1/2 mv squared, the velocity, which we write here as x dot squared. And we know this to be, let's see, we need this one here. Wrote too many dots too early, didn't I? Yeah, 1/2 mx dot squared. So if we square x dot, it gets rid of the minus sign. So we have a m, sorry, that dot's supposed to be there. I do apologize. So we have a m omega over 2 cosine squared omega t plus delta. And that should be right, isn't it? We have to square a. So that squares these two. I'm just trying to write all the squares so they're in the same place for ease of viewing. Square this bad boy up here. A squared, omega squared, cosine squared, divide by 2. Okay, now let's look at the potential energy. So you can also take this as a definition of the harmonic oscillator if you want. We know that the potential energy is just 1/2 m omega squared x squared. Why is this? What is the motivation for this? Well, basically, we know that f is the minus derivative of the potential with respect to x. And we also know that it's equal to minus kx. So if you integrate it, you can obtain this where k is a spring constant. It relates to omega by omega is equal to the square root of k over m. And if we wanted to eliminate k, we would write this force as, let's see. So omega squared multiply m omega squared. So force would be minus m omega squared x. But nobody really remembers it in this form. Everybody remembers it with the k's, and then you can get rid of them later if you want. So you integrate this equation, it should tell you, upon canceling the minus signs, dv by dx is equal to m omega squared x. And of course, we just integrate. We take the x to the 1 power, make it 2, and then the v of x is now 1/2 m omega squared x squared. So there. That's just a short derivation of why the potential should be the way it is. And let's proceed. So we have the kinetic and the potential energies. All you have to do is add them together now. Just add them as follows. Okay, so we have E is just going to be the kinetic energy plus the potential energy, which is, I guess we can do one more simplification here. Okay, so we have m a squared omega squared over 2 again here, since we have to actually square the original function x. And it's exactly the same, except it's going to be sine squared omega t plus delta. So what I did there was just take the constant 1/2 m omega squared, go up here to our x definition, square that, and you can actually see where this is going. We have a sine squared and a cosine squared. So let's see what happens here. Constant can factor out. And now we have cosine squared omega t plus delta plus sine squared omega t plus delta, which of course we know from high school is equal to 1. The total energy is just equal to m a squared omega squared over 2. Now we want to take the time derivative here, but wait, there's actually no x's or anything in the final answer. It's a constant. So if we look at our time derivative of E, which is, dE by dt, which is going to be the time derivative of this crap that we just had up here. I'm not seeing any times here, so the mass should certainly not depend on time. It's just, so mass on a spring, mass is going to be the same. The amplitude doesn't depend on time because we set the amplitude at the beginning and it always returns to the same amplitude at the end. The frequency is the same as well, since it just oscillates with the same frequency forever. So this is just 0. So we have shown that energy is conserved for the harmonic oscillator, as it should be. This is just a check that the harmonic oscillator behaves the way that we should think it does. Incidentally, it also behaves this way for the quantum harmonic oscillator, which we won't cover in this video. But you would start by defining the harmonic oscillator potential as 1/2 omega squared x squared with the corresponding operator definitions of the kinetic energy and go from there. If you enjoyed this, want to see more physics, please subscribe to my channel. I'll see you next time.